Okay, now it's time to move on to the null space. Null space is based on the solutions of Ax equal to 0. The system of linear equations that we dealt with mostly had Ax equal to b being a constants vector. But in the special case, when the b is a 0 vector, then that set is called homogeneous system of linear equations. And the solution set of that system is called the null space of A. So what that means is that a linear combination of the columns of A is going to give you 0. If that has a solution that is not trivial, obviously, if all xi's are 0 here, you will get a 0 vector here. That is what we mean by a trivial solution. If there are some solutions where some of the xi's may not be 0, but then the linear combination is 0, then that would mean that there is a non-trivial null space. What does that also mean? It means that there is a linear combination of the columns of A that gives you 0 vector with not all scaling factors being 0. That means the columns of A are not linearly independent. The matrix A is singular. It is rank deficient. Nullity is non-zero. So many different ways of saying it. But in this case, we are actually looking at the null space. So the null space being non-trivial, meaning it's got vectors that are not merely 0, but some other vectors inside, would mean that the columns of A are not linearly independent. And of course, the definition of the null space is the set of all such vectors. It's called the solution set, and that would be the null space. So formally, null space of A is a set of vectors of the kind x such that Ax equal to 0. Now you can understand that if x1 is a member of null space and x2 also is a member of null space, then any possible linear combinations of x1 and x2 will be a member of null space, because that linear combination also will evaluate to 0 under the application or the transformation of the matrix A. So it is really a subspace. Now let's look at the significance of null space. First of all, let's figure out the dimension of the space containing the null space, which is a subspace. As you know, in Ax equal to b, x is a member of Rn. X has as many elements as columns of A because it's Ax. So the columns of A will have to be equal to the number of rows of x. And remember, null space is a solution set. Any one vector inside null space can form a potential vector x in Ax. So null space is a subspace of Rn. It could in principle be all of Rn, but that is a very special matrix. Can you tell me what that matrix is? It's a 0 matrix. If a rank 0 matrix, its nullity, which is the dimension of the null space, will be n. Now the second thing to know is that Ax equal to 0 implies that x is orthogonal to every row of A. Take a row of A, call it R transpose because it's a row vector. So R would be a column in a matrix of the same size as x, same dimension as x. So you can take a dot product. So that would be Ri transpose x. Ri transpose x would be the ith row of this product. Ri is the ith row of A multiplying with x. That would be the ith row of the product. And that is 0 because on the right hand side you have all zeros. So Ri transpose x is 0. That means x, if x is a member of the null space, is orthogonal to every single row of A. That is interesting. So the rows of A are orthogonal to any vector that is a member of the null space. Rows of A are of course the columns of A transpose. Any possible linear combinations of the rows of A also will be orthogonal to the null space because that is how linearity works. So null space really is orthogonal to the span of the rows of A, meaning the span of the columns of A transpose. And that span is what we're going to call the row space very soon. But before doing that, let's look at the null space in slightly formal fashion. I have color-coded different spaces here. So the column space was red, the null space is going to be purple, the row space is going to be green, and the left null space is going to be blue. So let's take our favorite matrix, general matrix, A, m rows and n columns, and it's got a rank R. So set of all solutions to the homogeneous equation Ax equal to 0 is what we call the null space, the solution set. And what's the dimension of a null space? That is the number of linearly independent columns in the null space. That would be, as you shall see, the number of free variables in the matrix A. That means if you have n columns, r of them are pivot columns, n minus r of them are free variables. So the dimension of the null space is n minus r, and that is what we call the nullity of the matrix. So rank is r, n is the total number of columns. So the rank plus nullity is going to be the number of columns. And what is rank? Rank is the dimension of the column space. So the dimension of the column space plus nullity is the number of columns. So it's just another way of saying it. I am saying it in different ways because the statement that I just made is the famous rank nullity theorem, but it's kind of obvious when we approach it from this angle. Rank plus nullity is the number of columns. Now, the basis for the null space would be the special solutions coming from the free variables, and that, as you remember, is a bit harder to compute. It's not as easy as taking the pivot columns of A. The containing space, of course, is Rn, the input space. The statement is null space is a subspace of Rn, the input space, with a dimension n minus r, which is also called the nullity. So let's compute it for one matrix here. This is a matrix that we went through in a column space computation. As you can see, this will turn out to be a rank 2 matrix. 3 rows, 4 columns, rank is 2. So A is a member of R3 by 4. So null space lives in the input side, the number of columns. So null space is a subspace of R4, and its dimension is the nullity. We know that the number of pivots is 2. So how many columns are there? 4. What's the nullity? The number of free variables. That would be 4 minus 2, that is 2, and that's going to be the dimension of null space. Now, to find the basis takes a bit more work. Let's go through the solution here. But if you remember, going from A to its RREF, we perform row operations. Row operations are like equation manipulations without changing the solutions to the equations. So A and R, which is what I call the RREF, will have the same solution set. In particular, Ax equal to 0 and Rx equal to 0 will have the same solution set. But remember, Ax equal to B and Rx equal to B will not have the same solution set, because when you perform the row operations on A to get to R, you're actually messing with the constant side also, the augmented matrix. So what you will have once you have R here is not going to be B. If you started with Ax equal to B, it's going to be some B prime. So the solution set for Ax equal to B and Rx equal to B are not the same. But when you have Ax equal to 0, whatever equation manipulations you do, the right hand side is not going to change. The constant is always 0. So Ax equal to 0 and Rx equal to 0 will have the same solution set. So it's easier now that we have RREF to solve Rx equal to 0. So let's do that. So R is that, Rx equal to 0. Free variables, as you can see, are the ones corresponding to the columns without pivots, columns 2 and 4, x2 and x4. So we have from the second row, x3 plus 3 times x4 equal to 0. So that tells you that x3 is equal to minus 3x4. From the first row, we have x1 plus x2 plus 3x4 equal to 0. So x1 is equal to minus x2 minus 3x4. Now the solution, the way I did it here, you can just say x1, x2, x3, x4 is equal to minus x2 minus x4 coming from here, that is x1. x2 is just x2 minus 3x4 coming from here, and x4 is just x4. Now remember, x2 and x4 are free variables. That means you can choose them to be anything. From this matrix here, let's split them up. x2 terms together, so x2 with a minus 1, x2 with a 1, and then 0, 0. pull out the x2 here, then x4 with a -3, x4 with a -3, pull out x4 there, and you get that. And then this is something that you can choose to be anything. Later we will just call it t1 or t2, any number, and that would satisfy the requirement that Rx be equal to 0. You can verify that. So all such linear combinations will form the null space. What does that mean? Null space is a subspace of R4 because each vector has got 4 components. Dimension is 2 because there are 2 basis vectors, and the basis would be these 2 vectors. So this is one way of solving it. Now let's kind of review this complete solutions business because you may have forgotten it. Remember that a rank efficient matrix may have infinite number of solutions because there is at least one free variable. So it's got either infinite number of solutions or no solution at all if the equations happen to be inconsistent. That is, if there is a row of zeros equaling a non-zero on the right-hand side, constant side, then of course we cannot solve. So you have more columns than rows, more variables than equations. So you have free variables and then you have infinity of solutions. That also means if you have infinity of solutions, the null spaces are non-trivial. That means null space is not just a 0 vector. Null space will always have the 0 vector because Ax equal to 0 will always have a solution when x equal to 0. So Ax equal to 0 is never inconsistent because the right hand side is already 0. So there's no 0 equal to non-zero possible because right hand side is already 0. So infinity of solutions when there is a non-trivial, which means non-zero x such that Ax equal to 0. Why is that you have infinity of solutions? Let me illustrate that this way. Well, it turns out that I cannot tell you now because we use the green row space, which we haven't defined yet. We will circle back to this once we have done enough work in terms of row space. But let's take an example to look at the complete solution as a review. So here is a system of 2 equations and 4 unknowns. So if you write down the augmented matrix, you get that. Subtracting 2 times the first row from the second row. The first 2 columns will have zeros in the second row. And then you have pivots in here and here. RREF, after normalizing the pivots and then getting rid of this, you get that. Fine. So you have 2 equations there. x1 plus x2 plus 5x4, x1 plus x2 plus 5x4 equal to 3. No x1, no x2. x3 minus 3x4 equal to 3. So 4 variables, only 2 equations, x2 and x4 free variables, no pivots there. Now let's go through the algorithm for finding the solutions. What we do is to set the free variables to 0 to get a particular solution. Remember, free variables, you're free to set to any value. So you can set them to 0. So x2 and x4, you can set them to 0. That would mean x1 equal to 3 and x3 equal to 3 because x2 is set to 0, x4 is set to 0. So x1 is equal to 3 and x3 equal to 3. So that's a particular solution, what we call x particular or x parallel for reasons that will become clear later. So that looks like this. Then, in order to get the so-called special solutions, solutions that belong to the null space, which we'll call xs or x perpendicular, because this was parallel. So you set the right-hand side to be 0 because that's what we're looking for. Again, set the free variables to convenient values so that you get the non-free variables. So set x2 equal to 1, x4 equal to 0. So that is the first step. Those are convenient. Then you get x3 equal to 0. That's a special solution. x2 is already set to 1. Then set x2 equal to 0 and x4 equal to 1. That's another set. So x1 plus x2, which we set to 0, plus 5x4, which we set to 1. So x1 plus 5 equal to 0. Then x3 minus 3 because x4 was set to 0. So there's a special solution too. So looking at it, you have a particular solution. Then you have a special solution coming from the fact that you have x1 equal to minus 1 from that equation. x2 was set to 1. x3 turned out to be 0, then x4 was set to be 0. So that's the first special solution. Then the second one, x1 turned out to be minus 5, x2 was set to be 0 because that's a free variable. You can set it to anything you want. x3 turned out to be 3 from this equation, and x4 was set to be 1. So that is the complete solution. So the null space is going to be these guys because they will always give ax equal to 0. If you take x to be any one of these linear combinations, then ax is going to be equal to 0, and that's what we call x perpendicular. X parallel was the particular solution by setting the free variables to 0. So this is the procedure. This is the algorithm that you have to use to arrive at the complete solution. Again, x parallel is going to be a member of row space, which we haven't fully defined yet. We will get there in a second. But x perpendicular, which is what we were trying to compute, is a member of the null space. Now, let me just highlight the solving procedure. What we did was to find the RREF through Gauss-Jordan elimination on the augmented matrix. Then you ignore the free variables, meaning just set them to 0. The variables corresponding to the pivotless columns are ignored by setting them to 0. Then solve for the non-free variables. That will give you x parallel or a particular solution. Then for each free variable, you cycle through them and you try to solve the homogeneous augmented matrix, meaning just set the right hand side to 0. Set each free variable to 1 in sequence and the rest of the free variables to 0, and then keep solving. So for each free variable, you'll get a set of solutions, and those solutions are special solutions. And also that will be one basis of your null space. So that's the procedure. And then you will write the complete solution as the particular solution plus the special solutions with any scaling factor. The particular solution is in green for reasons that will become obvious to you in the next video. And the next video is actually the row space, which will be in green.